Hey, I'm Rage. Welcome to my channel. Let's have a look today on Bitwise Operations. I have already created ourselves an overview on different Bitwise operations that are available to us. And let's start at the top with the Bitwise NOT operation. The Bitwise NOT operation toggles the bits and the bit field, which looks like this. Let's say we have 001 00110. If we apply the bitwise NOT to it, we get all zeros being turned into 1 and all ones being turned into a 0. 1 1 0 1 1 0 0 1. So far so easy, right? The next on the list is the bitwise AND operation. And the bitwise AND operation combines two bit fields in the way that it sets a 1 bit where both bits and both inputs at the same position are equal to 1. So if we perform an OR between 0 0 1 0 0 1 1 0 with 0 1 1 1 0 0 0 1, we set everywhere 1 where both bits are 1. As in here, if both are 0, we have a 0. If only 1 is a 1, we get a 0. But as soon as we have both bits and inputs a 1, we set a 1 in the output. I guess this is also clear. Then we have the bitwise OR, or the bitwise inclusive OR, and the bitwise OR also combines two bit fields in the way where every time at least one of the bits in the inputs is 1, will result the 1 in the output. Let's have a look. From the front, we have no 1 at all, we get a 1. Okay, we have at least one bit, we get a 1. We have two 1s, well, it doesn't matter, at least one bit has to be 1, so we place a 1 in the output as well. Again a 1, because we have at least one 1. We have no 1 at all, we set a 0, and we have again at least one 1, we get a 1, the same for the next one, and the same for the last one. The next on the list is the bitwise exclusive OR, and this is a little bit special. It combines as well two inputs, but sets a 1 in the output where both bits are not equal in the inputs. Therefore, 0 and 0 are equal, we set a 0 in the output. 0 and 1 are not equal, so we set a 1. 1 and 1 are equal, we set a 0. 0 and 1 are not equal, we set a 1. 0 and 0 are equal, we set a 0. And 1 and 0 are not equal, we get a 1. Same for the next, and same for the last one. I believe these are the most simple ones. Now let's have a look at our left and right shift operations. The left shift operation shifts n bits towards the most significant bit. This means that we have on the left hand side a bit field, as we had in the others, but on the right hand side we specify a number of bits to move, to shift. What happens is it will take the input bit field and moves all the bits 4 positions to the left. I have underlined the bits that get moved to the left, and the specialty here is that, of course, the leading 4 bits get out of bounds of our bit field, right? If we have 8 bits, let's say we have a byte as shown, then we have nothing where we can move the bits into, right? The first leading ones. Therefore, they get just discarded. And on the other hand, by moving them 4 positions to the left, we create a gap on the right hand side. And this gap we just fill or get just filled by 0 bits. Therefore, we can see that the underlined ones move correctly 4 positions to the left, and the now empty fields get replaced by zeros, and the ones that were in the first 4 positions at the start are just discarded. The similar thing happens to the bitwise right shift operation, just into the other direction. The bitwise right shift operation shifts n bits towards the least significant bit. And again, I have underlined again the 4 bits that we want to move to the right. We move them to the right. The last 4 bits get discarded, they fall out of bounds, and the gap on the left side gets filled with 0 bits. But how these operations are now useful for us? Well, before we can picture this, we need to agree on one thing, that for us a byte is no longer a byte, it is a combination of 8 on-off switches. If we have a byte which has these bits set, we can say that we have option 1 active, option or switch 3 active, the 5 and also the 7 are active. If I want to know now all the options that are not active, I use the bitwise not, which gives me a true for all options that are not active. If I want to check if a specific option is set, then I use a so-called bit mask, which is a bit field of the same length, where all the bits or switches are set that I am interested in to know if they are set. So if I want to know if option 3 is active, then my bit mask will look like this. The bit that I am interested in is set to 1 and the others are set to 0. What I then can do is I take my bit field from above and perform a bitwise AND with my bit mask. And as we know, The result of this operation results in a 1 bit wherever both left-hand and right-hand operands have a 1 bit in the same position. Therefore, if my bit is set, I should receive back, as a result, the bit mask that I initially used as right-hand operation to my bitwise AND. So, these are equal. Then I can say surely that the bits that I requested or checked against my bit mask are set if the result again is my bit mask. But we can also activate and deactivate specific options. Let's say I want to deactivate option 3. Then I can use the exclusive OR with the same bit mask on my bit field. And the result will, as we know, be a 1 wherever both are not equal. So 0 and 0 are equal. And then we have 2 times not equal. We have equal. We have equal, equal, and not equal. And we can see that this exclusive OR with our bit mask for option 3 remove option 3 from our initial bit field. It's gone. It's now a 0. If we now want to put it back, we take this bit mask and apply a bitwise OR with option 3 set. And as we know, the bitwise OR sets a 1 where at least the 1 bit is 1 in the operands. So we get a 0, a 1, a 1, a 0, a 0, a 1, a 0, a 1, and we can see we have activated again our option 3. So, what we can effectively do in code, whenever we have multiple options where we just want to say if they are active or not, we don't have to put a bunch of booleans. We can just get a bit field of the proper length, can be 1 byte, can be 2 bytes, 4 bytes, 8 bytes, and just store them or just consider our on-off switches in those bits, and use the techniques that I have showed you on the right to query the different bits set, not set, deactivate them, activate them with the bitwise operations. This can save us lots of memory. Okay, let's have a look on our use cases for left shift and right shift operations. In my opinion, the most useful thing to do with them is to extract bytes out of larger types. What I mean with that, let's assume we have a 16-bit number and what we want to do now, we want to separate it into 2 8-bit numbers, where one 8-bit number represents the left byte and one 8-bit number represents the right byte. How we can do this? The right one is easy because what we can do to get the right byte, we already covered above here. We can apply a bit mask. Where all the bits that we are interested in are set to 1. And in hex, because when we code, we would usually not write the byte out, even if we can. We would write it either FF, which is the same as for 2 bytes, right? And then what we get is we zero out the first byte. We are left only with our right byte, and this we can now safely cast to an 8-bit number, and we have our 8-bit number for the right byte. But what about the left one? We do practically the same, but before we shift the whole 16-bit number 8 bits to the right. Right? 8 bits are 1 byte, so we move the whole byte to the right, which will look like this. And we can again now safely cast to an 8-bit number and we have both bytes separated into 2 numbers. Let's say we have 2 8-bit numbers and want to create one 16-bit number out of them. Let's reverse it. First of all, what we're going to do, we take the former left, we take the left number or the left byte that we want and shift it 8 bits to the left. However, we have first to make sure that we have a 16-bit number, right? We will cast this to a 16-bit number, which will give us back this. Then we shift the whole thing to the left by 8 bits. We end up with and what we then do, we take our right hand byte as a 16-bit number and OR them into the first number, and we get our combined 16-bit number. And this we use quite a lot in the future. However, I want to mention two things specific to the left and right shift operation. First of all, let's suppose we have one single byte with the last bit set 1. In binary, this is a number 1, right? So, what happens if we move this bit 1 position to the left? Well, we get a number 2, right? 1 0 in binary is a 2 in decimal. Now let's do this again. What do we get? One 0 0 in binary is a 4. We see the pattern, right? So, what we can already say that left shift by 1 position or by 1 bit is equal to a multiplication with 2. And therefore, when we shift right by 1 position, we have an integer divide by 2. And a right shift by 1 bit is the same as an integer divide by 2. Why integer divide? Integer divide is just an operation where you divide two numbers and discard the remainder, right? If you have integral numbers, you cannot specify or display or grab the decimal part of the number, right? Therefore, an integer divide is always a division that just discards the remainder. And that's it about bitwise operations for today. The last part is very important because I believe it's incomplete if I don't mention this. Therefore, in the next video, we will make use of this stuff. I hope you like it, or you liked it, and see you next time.